Welcome once again into the class of topology, and in the previous two videos I have explained directed sets and the basic definition of net and basic concepts like eventually in Y, frequently in Y, residual subset, cofinite subset, and now we are moving ahead towards the convergence of a net. So, convergence of a net, this topic we will learn today. We will try to understand it, the basic concept. As I have explained in the previous videos, that net is a generalized sequence. Net is a generalized sequence, and in some books, nets are also known by this name. And nets are also known by the name Moore-Smith sequence. Moore-Smith sequence. It is another name for nets. So since nets are a generalized form of sequences, so the convergence of sequence and the convergence of nets must be a little bit similar. And yes, it is. So you know about the convergence of sequence. So we'll start with the convergence of sequence, and then from there we'll obtain the definition of convergence of the net. So we know that if xn is a sequence, if xn is a real sequence, then we say that xn converges to x naught if for every epsilon greater than 0 there exists some m natural number such that xn belongs to this open interval x naught minus epsilon, x naught plus epsilon for every n greater than or equal to m. This is the definition of convergence of the sequence. And from here we will derive the definition of convergence of net. So it is to be noted that what this x naught minus epsilon, x naught plus epsilon interval is. Actually it is a neighborhood of x naught in real line. So if we are moving in the nets, we are not having this real line, we are not having this real interval. So this real interval will become the neighborhood of the point x naught. So you can say n, where what is your n? Your n is a neighborhood of the point x naught. That means n is a member of an x naught, the neighborhood system of x naught. So one point is here. Secondly, for sequence we use this symbol xn, and for nets we use f of a. So I am writing here fa, and suppose fa converges to x. The symbols are going to change. fa is converging to x. Then xn here will be replaced by fa, and x naught is replaced by x. Also, for the sequence, the domain is the set of natural numbers, and for nets, the domain is the directed set. So this n will be replaced by the directed set D. Here also, this fa belongs to this n. This is not the set of natural numbers, but this n is the neighborhood of x naught. Also, this was fa, earlier it was xn, so we are having here n, and now we are having here a. In directed set, we replace this m by a naught, so this m will be replaced by a naught, and there is no need of this epsilon now. In fact, here we will have if n belongs to an x naught, this condition. So this I am going to replace from here to here, and here you are having the definition of convergence of the sequence. So convergence of nets. So if fx d greater than or equal to is a net with d the directed set as the domain, x as the range, this is the binary relation which we are using, that means follows, then the net fa is said to converge to a point x if for every neighborhood n of the point x, not x naught now because fa is converging to x, so for every neighborhood n of the point x, there must exist some a naught in D such that whenever a follows a naught, your fa must be in the neighborhood. So in fact what we want to say that there is your x, and in x you are having this small x, you are having a neighborhood of x, and as you proceed, as a follows a naught means a is greater than or equal to a naught, that means you are going ahead. So this is f1, f2, f3, so you are moving ahead. As you move ahead, your images fa means say fa1, fa2, fa3, fa4, fa5, fa6, fa7, fa8, fa9, fa10, fa11, fa12, fa13. So at some stage, so here the stage comes after fa12. Now each image now fa14, 15, 16, 1000, 2000, 3000, million, 2 million, now they are in this neighborhood. You may make this neighborhood smaller. The stage may go a little bit ahead, may not be at 13, may not be at 17, maybe at 17. If you take more small neighborhood, the stage will go more ahead. It may not be at 17, it may be at 100, it may be at 200, it may be at a 700. So there will be some stage. Such that after that stage, after that particular a naught is a member of D. After that particular a naught, whatever a is there, a greater than or equal to a naught, your fa must be in the neighborhood, and whatever the neighborhood and you take for the point x. So this is the definition of convergence of net, which I am going to write now properly. So proper definition of convergence of net. So let fxd greater than or equal to be a net, and let x be a point of x, then f is set to converge to the point x if for every neighborhood n of x there exists a naught in D such that whenever your a is greater than or equal to a naught, that means a follows a naught, we have fa belonging to n. The last line I can also write it as, it is correct, it is not wrong, but it can also be written like this, such that fa belongs to n for every a greater than or equal to a naught. So whenever your a follows a naught, your fa must be in the neighborhood, and whatever n you take, your a naught, the stage may change, but the situation will be there, and then we say that the net f converges to the point A. So this is the definition, and let us now see some examples. Let us have some examples. So it is a basic question in our minds. What will happen in case of discrete or indiscrete topology? So yes, these are very good questions, and we will discuss these questions first. So if your net fxd greater than or equal to be such that this x is having in discrete topology, then for every x belonging to x, your fa converges to x. That means the point of convergence is not unique. Your net converges to each point of the set x. Whatever the point small x you take from the set x, your fa will converge to x. Why? The reason is that now if you talk about the neighborhoods of x, this is in discrete topology, and in discrete topology there are only two open sets phi and x, and the only neighborhood of every point x here is the set x itself. For every x you have only one neighborhood, x. So your n will be replaced by x, and there is no other possibility. This is the only possibility. X is the only neighborhood of the point x. And what is the condition you require? You require your fa belong to n, and n means x. Your fa belongs to x for every a greater than or equal to a naught. There should be some a naught satisfying this condition. And fa belongs to x is true for all a, right from the starting. No need to wait for any stage. Right from the starting, because your net is from d to x. So f of a belongs to x is that sure for every a. Whatever a you take from the set directed set D, your fa is going to be in x. So fa belongs to x for every a. So you, even if you take your a naught as the initial point of your directed set, the very first element of the directed set, your fa will belong to x for every a following that element. So your net fa converges to x because this x was the neighborhood of the point x. So that means for in discrete topology, whatever net you take, the net always converges to every point of the topological space x. This is the case of in discrete topology. And one thing here you have seen that in case of sequences, the point of convergence is unique, but here the point of convergence is not unique. You may have many and maybe infinitely many points of convergence. So this is the basic difference between the sequences and the generalized sequences, that means the nets. So this was the case of in discrete topology, and let us see now what will happen if we are having discrete topology. So now our fx d greater than or equal to is a net, and this x is having discrete topology. And for discrete topology, we know that every subset of x is an open set. So if you want your net f to converge to a particular point x naught, if you want that f should converge to x naught, then by definition of convergence of nets, what will happen, that there should be some a naught in D such that your fa must be in every neighborhood. So here I am taking the smallest neighborhood. This neighborhood I am taking as the singleton x naught, the singleton set x naught. This is also a neighborhood of x. This is also a neighborhood of x. So for this neighborhood, there must be some a naught in the directed set D such that your fa belongs to x naught for every a that follows a naught. And fa belonging to the singleton set x naught means your fa is equal to x naught, because there is only one element. That means after some stage, if the net f is to converge to the point x, after some stage, each and every image of the net must be equal to x naught. So the case is different now. Now it is that here it is your x naught. Your fa naught may be here, fa1, fa2, fa3, fa4, fa5, fa6, fa7, fa8, fa9. But at some stage, all FAs must coincide x naught. That means if your a naught is suppose a 1000, then f a 1001, f a 1002, f a 1003, and so on. Each one should be equal to x naught, because you are saying that after a naught, if your a is following a naught, that means if a is greater than or equal to a naught, then your fa is equal to x naught. So if your a naught is suppose a 1000, then whenever your a is greater than a 1000, if your a is a 1001, then fa 1001 should be equal to f naught, fa 1002 should be equal to x naught, fa 1003 should be equal to x naught, and so on. That means after some stage, each and every image of the net must coincide with x naught. This is the case of discrete topology. And now we are moving towards the first theorem of nets. So write down the statement of the theorem first, and then we will move on to the proof. So this is the first theorem on nets which we are going to prove. Statement is, let f be a net in x minus y where x tau is your topological space, and y is a subset of x. Let f be a net in x minus y where x tau is the topological space and y is a subset of x. Then y is tau open if and only if no net in x minus y can converge to a point of y. Here you are having if and only if. That means you will have to give the direct proof as well as the converse part. So once, for the first part, we will suppose that y is tau open, and then we will show that no net in x minus y can converge to a point of y. And for the converse part, we will suppose that no net in x minus y can converge to a point of y, and then we will show that y is tau open. So this is the statement of the theorem, and now we are moving towards the proof of the first theorem on nets. So for the direct proof, let y be tau open. Let y be tau open, and we want to prove that no net in x minus y can converge to a point of y. This we want to show, that no net in x minus y can converge to a point of y. So suppose, if possible, there is a net in x minus y that converges to a point of y. Suppose if possible, there be a net in x minus y that converges to x naught belonging to y. So your let this net be f. Now your net f is converging to x naught, and by definition of convergence, for every neighborhood of x naught, f must be eventually in that neighborhood, because after some stage each element is belonging to that set, that means f is eventually in that set that we have defined in the previous video. What is the meaning of eventually in? So this means f is eventually in every neighborhood of x naught. X naught is a point of y, and y is given to be tau open, so that means y is also a neighborhood of x naught. And since y is also a neighborhood of x naught and f is eventually in every neighborhood of x naught, then this means f is eventually in y. F is eventually in y, and f is eventually in y means there exists a naught and d such that fa belongs to y for every a that follows a naught, that means greater than or equal to a naught. And this is a contradiction. Why? Because you are saying that fa belongs to y after some stage. After some stage, each and every fa is belonging to y. But your net is in x minus y. Your net is, look into this picture. Here it is your x, it is your y. Your net is in x minus y. That means your net is here. Net is here means all the images are in this portion, the dotted portion. FA1, FA2, FA3, FA1 million, FA2 million, FA, everyone. All the FAs are in this dotted region. And here you are saying that FA belongs to Y after some stage. This is a contradiction. And this is a contradiction because we have supposed that there is a net in x minus y that converges to a point in y. So our supposition was wrong. Hence, no net in x minus y can converge to a point of y. So this was the direct proof. And now we are moving towards the converse of this theorem. Conversely, let no net in x minus y can converge to a point in y. And what we are to show? We are to show that to prove y is tau open. We have to prove that y is tau open. Suppose y is not open. Let, if possible, y not be tau open. Now move on to the basic concept of openness of a set. If a set is open, then it is neighborhood of each of its points. Now we have supposed that y is not tau open. That means y is not neighborhood of each of its points. That means there will be at least one point in y such that y is not a neighborhood of that point. So therefore, there exists x naught in y such that y is not a neighborhood of x naught. Now, if y is a neighborhood of x naught, then there exists at least one open set containing x naught, or you can say there is at least one neighborhood of x naught that wholly lies within y, that completely lies within y. But y is not a tau neighborhood. Now, y is not a tau neighborhood of x naught. Now, that means each neighborhood of x naught intersects x minus y. Because it is not completely in y, that means it intersects x minus y. So therefore, for every n belonging to an x naught, the neighborhood system of x naught, for every neighborhood of x naught, we have n intersected with x minus y is not phi, because every neighborhood now intersect this. If a single neighborhood has empty intersection with this, that means the neighborhood completely lies within y, and that will make y an open set. But y is not tau open, so every neighborhood of x naught will intersect x minus y. So this intersection will be non-empty. And if this intersection is non-empty, then there must exist some element, say xn, belonging to this intersection. And now we define a function. Define f from your d to x such that f of x minus y, take it as x minus y, such that f of x naught, f of a is this xn, f of n, is this xn. Actually, here this D we have taken as nx naught. This directed set we have taken as the neighborhood system of x naught, and we know that nx naught with this subset of binary operation, this is a directed set. We have proved it in the previous video. So I have taken this directed set at neighborhood system of x naught, so its members are n. So f of n is equal to xn. I have defined like this because this xn belongs to x minus y, and this xn also belongs to n. This xn also belongs to n. So I have defined this function. So since for this function your domain is a directed set, this is automatically a net. So we have defined a net now, and we will show that this net, we were given that no net in x minus y can converge to a point of y. This is a net in x minus y because the image is in x minus y. But we will show that this net converges to x naught, and x naught is a point of y. And this will be a contradiction because a net in x minus y is converging to a point of y, whereas we are given that no net in x minus y can converge to a point of y. So this will be a contradiction, and it will prove that your y is tau open. So first we will show that claim now. Claim this net f converges to x naught. And if you concentrate on the definition of convergence of nets, here the definition is, look into the definition first, then I'll make required changes. For every neighborhood of the point x naught, there must be a naught in D such that f of a belongs to n for every a that follows a naught. This is the basic definition. Here your D is neighborhood system of x naught. N is also in an x naught. Your a naught is in x naught. So your a naught, you can replace it by again some w, some neighborhood of x naught. So this a naught will be replaced by w here too. And this follows is now subset of, because nx naught is a subset of. And this a is also coming from this neighborhood system. So here again you must have some v. So here you must have f of v belonging to w. This w is coming from here. So sorry, this is n. So this definition will have to be followed now. This type of situation we need here. This type of situation we need here. So how we will arrive at this situation? So look at, let V be a tau neighborhood of x naught. Then for every w belonging to nx naught, that means for every w which is a neighborhood of x naught, such that w follows v, a greater than or equal to a naught, w follows v. This is your a, this is your a naught. We have f of w, that means fa, and this fw by our definition is xw, xn, and it belongs to w intersection with x minus y, and this is a subset of w, and w is a subset of v. So combining this, I can say I'm rewriting this now. For every w belonging to nx naught, for every V belonging to nx naught, there exists W in nx naught such that f of W, a little bit change, there exists V, you can say there exists V such that for every W, f of W belongs to V, f of W belongs to V. So this FW belongs to V. For every W that follows V. This is your neighborhood now. This V and this V you need not to confuse, because this V is the neighborhood and this V is acting like A naught and A. So A greater than or equal to A naught, your f of, if you concentrate on this, you will be able to understand what we want to prove. F of A belongs to N, here it is N, neighborhood. F of A belongs to N for every A that follows A naught. Here it is A naught. Here it is neighborhood, here it is A naught. So this is the definition of convergence. So that means your net F converges to x naught, but x naught is a point of y, and it is a contradiction because we are given in the hypothesis that no net in F can converge to a point of y. And this is a contradiction because we have supposed that y is not tau open. That means y must be tau open. And this was the proof of this theorem. With this proof, we are closing this video here. In the next video, we will have more and more theorems on nets and filters. Till then, thank you once again.